Hello everyone, this is Ximeng Yu from Georgia Tech. It's my great pleasure today to present the resistive random access memory (RRAM) for computing memory. We are going to discuss how to use RRAM for inference to training of the neural networks. Most of the presentation materials today can be referred to this paper presented in the IEEE transaction on CAS 1. This is an outline of today's presentation. First, we will give a brief background of computing memory and RRAM technology, and then we will discuss the multi-level RRAM categorization at the array level using a test vehicle, and then we will present our benchmark results for the inference and then training performance. And then finally, we will show a prototype chip using 40nm RRAM process to implement a computing memory macro. And finally, I will summarize and give an outlook. This is the background of the research, as we are motivated to develop the hardware accelerators for artificial intelligence. So we see different options. First, GPU still dominates the training in the cloud, and FPGA is becoming a good candidate for the inference, especially for the faster prototyping of the AI model. And also we see the TPU, like digital ASIC solution, is ramping up in cloud as well as the edge. If we look at the energy efficiency of those existing solutions, like the conventional GPU or FPGA is about 0.1 TOPS per watt. This is essentially throughput divided by the power, and then the TPU, like ASIC design, can improve the energy efficiency to 1 to 10 TOPS per watt. But if we want to further boost the energy efficiency to 10 to 100 TOPS per watt, then we will have to employ some of the analog or the mixed signal techniques to perform this computing memory to reduce the data movement, therefore further improve the efficiency. But of course, the analog approach may suffer from variations and noises and no precisions, therefore there will be a question mark whether the inference or the training accuracy can be as good as a digital counterpart. We will try to address those questions later in the talk. So here, the bottom line is that if we want to further improve the energy efficiency of the hardware acceleration in terms of TOPS per watt, analog computing memory, possibly with non-volatile memories such as resistive random access memory (RRAM), is a promising compute paradigm, especially for the edge inference. And later, if we can enable the adaptive transfer learning on the edge devices with possibly unlabeled data set, that will be a further attractive motivation to develop this kind of hardware platform. Let's first review the basics of the computing memory. Essentially, this is a mixed signal compute with the analog approach within the memory array. So here, the input vector from the neural network can be loaded in as voltages in parallel to turn on multiple rows of the memory array. And the weight of the neural network can be mapped as the conductance of those memory cells. Therefore, the input voltage multiplied by the conductance will result in a current, and the current can be naturally summed up along the column. At the end of the column, the current sum represents the partial sum of the computation, and then we may later use the peripheral logic to reconstruct the significance of the weights if the multi-bit weight has to be used in the neural network. For example, if we have 8-bit weight in the neural network, but the memory array can be only 2 bits per cell, therefore we need 4 memory cells to represent the 8-bit weight through the digital shift and add after the ADC. And also we may need the mux to share the ADC among multiple columns if the ADC takes too much area. So the time multiplexing may be needed at the edge of the array. In terms of the memory technology that can support the computing memory, we can use the CMOS baseline, for example, 6 transistor or 8 transistor SRAM cell. or we can rely on the emerging non-volatile memory, like those resistive random access memory in this 1T1R format to implement a more compact solution of the weight memory. So in this talk, we are going to focus on the 1T1R based solution. Why RRAM for computing memory? First of all, RRAM is a two-terminal emerging non-volatile memory. Consists of the 3 layers of stack, the top electrode, metal oxide, and bottom electrode. So the resistance of this device can be changed depending on the voltage input. If we have a large voltage across this stack, there will be like oxygen vacancies generated to form a filament to conduct the current. Therefore, the device can be switched to a low resistance state. If we reverse the voltage polarity, then the filament can be ruptured. Therefore, the device returns to a high resistance state. On the right-hand side here, we show a typical representative bipolar switching IV characteristics of the RRAM device. So on the positive side, if the voltage is larger than the threshold, then the set switching will happen. So device switch from high resistance state to a low resistance state. If we reverse the voltage bias, the device switch from a low resistance state back to a high resistance state. The RRAM's benefits compared to the SRAM can be summarized as follows. First, as a same technology node, the RRAM 1T1R cell has a much smaller cell size than the SRAM's 6 transistor or 8 transistor layout. And also RRAM can possibly store multi-bit per cell compared to like 1 bit per cell in the SRAM. So potentially the RRAM can hold more weights on chip. For example, the deep neural network may need more than 100 megabytes capacity for the on-chip memory. And RRAM can have this potential to achieve all the models on chip. Therefore, we can eliminate or reduce off-chip DRAM access, which is a bottleneck for the energy consumption. And also, RRAM is one of the non-volatile memory. That means we can power off the chip without losing the data. Therefore, we can enable the instant on and off for the inference with the dynamic power gating. We don't need to reload the model as we did for the SRAM-based solution. And also, RRAM can be stacked in the 3D fashion at the backend of the LAN. Therefore, we can envision a monolithic 3D integration for the RRAM on the top tier of the CMOS. Industry has invested in the RRAM technology over the past 10 years, and RRAM is becoming technologically mature with boundary availabilities. For example, TSMC offering this 40nm RRAM process commercially, and also Intel reported their 22nm RRAM solutions as well. And there are many other RRAM vendors around the world. For example, Wenbang, Sony, Panasonic, they all have their RRAM solutions. So here we like to showcase RRAM design for the XNOR compute. This is one of the representative binary neural network. So here, this is our design. So we use 2 1T1R cells grouped together to implement the positive and negative 1 weight. And also the input positive 1 and negative 1 is encoded as a complementary data to the VLAN and VLAN bar. So here, the truth table tells you the compute output, essentially from XNOR computation. Because here, if the input is -1, weight is -1, then we're going to have a +1 output. And the effective resistance from the 2T2R bit cell will become a low resistance state. And you can also refer to the truth table to interpret the other logic functionality here. So as a result, at the end of the column, so we effectively count how many number of ones in the partial sum. And then we're going to use a pull up PMOS to basically interpret the output as a voltage, analog voltage at this node. So here we are going to use ADC to digitize the analog voltage for the speed line voltage. So depending on how many ones in the pull-down network through the resistor, we are going to have different speed line voltage. Therefore, we can sense the output depending on the precision of the ADC. And in this case, we use 3-bit flash ADC to perform the XNOR compute. So this design was implemented at 90 nanometer process using a one-bond RRAM technology based on hafnium oxide. And here we compare the chip performance with the previous design from a 55 nanometer process. So although we are at a legacy technology node, we still achieve better throughput and energy efficiency. Multiplied by the throughput, we interpret that as a figure of merit. The reason is that in this particular design, we can turn on all the rows simultaneously to perform the compute. In this case, we turn on 128 rows at one time to compute the partial sum, while in the prior work, only 9 rows can be turned on simultaneously. Therefore, we can further improve the throughput and the figure of merit. But we do see some degradation in the CIFAR10 accuracy. So typically for the CIFAR10 dataset, the software baseline can achieve 90% accuracy, but in our testing, only like 83% accuracy can be achieved. This is suffered from the noise and variations, as we will discuss later. Okay, next we are going to use this XNOR RRAM 90 nanometer test vehicle to characterize RRAM's characteristics at the array level. So first of all, we need to tighten the RRAM resistance distribution if we want to use it as multi-level memory. So here for the computing memory, what we care about is the distribution of the RRAM resistance, because any deviation from the mean value will be added up along the column as the partial sum current. This is unlike the multi-level memory for storage, where we only care about the tail-to-tail gap between two adjacent levels. So here we care about the deviation. To tighten the RRAM resistance distribution, we develop a protocol to further do the write and verify. So here I will skip the details of the write and verify protocol, but the idea is to converge the conductance through multiple write and read pulse sequences to converge the conductance to the target level. So here we show one fine-tune evolution of the RRAM resistance. So here, this is the target range, and then we can apply first the pulses, and then there will be out of target, and then we apply the second pulses. Sometimes we may overshoot, so we need to do this set loop and reset loop, and then finally we fine-tune the pulse amplitude to converge the conductance to the final target. So with this kind of approach, we can tighten the distribution of most of the cells in the array to this very tight range. So here, this is the final distribution after the 2 round write and verify loops with the variation like 3%. And here we show 4 levels of the distribution after the write and verify. So this can encode 2 bit per cell data. And here we do see that the intermediate state may have some tail bits, but most of the cells can be converged to the target level. So here the axis in the Gaussian scale. So here most of the cells are within the target. After we program the RRAM resistance to the target, then we may worry about the resistance drift due to the disturb, especially under the read stress. So this may influence impact the inference accuracy. So here we test the different resistance levels under the rate stress over the time, and we do see the resistance changes at high bit-line read voltage, especially intermediate data like the state 2 and state 3 may drift more gradually. So with this kind of statistics, we incorporate that into a VGG8 neural network for the CIFAR10 accuracy. We do see that we have to lower down the read voltage to like 0.3 volts to sustain like 10 to the power 7 cycles, read cycles before the accuracy collapse. So this imposes some limitations on the bit-line voltage we can apply during the consecutive read or the inference workloads. And also there is a concern of the data retention at higher temperature. So here with this test vehicle, we test the resistance or conductance at higher temperature up to 120 degrees Celsius. So here we measure the resistance as function of time, and at different temperature, we do see that the conductance drift over time. So here we show the mean value, and then the other plot we show the standard deviation. So the mean value of the conductance decreases, and also the deviation or the variation increases over time, especially at higher temperature. So here we did empirical modeling to model the mean value and the sigma as a function of the time at different temperatures through this formula. And then we can incorporate this model into the neural network simulations to estimate the accuracy degradation over time. And we do see that at higher temperature, the accuracy may degrade faster. And in this case, the CIFAR10 accuracy quickly drops after like 10 to the power 4 cycles of 10 to the power 4 seconds. Therefore, this is indeed a concern for the applications at higher temperature. But we have some solutions to mitigate this problem. To use a batch normalization parameters retrained for different temperatures to recover the accuracy loss. So there are some promises offered by the algorithm techniques. Next, we are going to show the benchmark results for the inference performance if we use RRAM technology. First of all, we like to introduce a framework for the benchmark. So here we use this DNN plus NeuroSym framework developed by our group to do the following benchmark. Essentially, this is a framework made in Python wrapped with the NeuroSym core in the C++. And here, the NeuroSym core is our in-house simulator to estimate the energy, latency, chip area of the circuit performances. And then this is wrapped around with the PyTorch or the TensorFlow machine learning packages. Therefore, we can reconfigure our chip architecture for different network structures. So here we support like VGG, ResNet, DenseNet, and so on, different kinds of neural network models for CIFAR10 or ImageNet dataset. And this is an open source tool available at the GitHub. So here are the links for the latest version, v1.3 for the inference, v2.1 for the training. So this is an overview of the framework structure. So basically, we can set up the neural network topology and structure in the PyTorch or the TensorFlow with the algorithm parameters like the precision of the weight, activation, and so on. And then we can introduce non-ideal device and circuit properties into the accuracy estimation. For example, we have shown earlier, the device resistance may drift over time, or the ADC may have limited quantization levels. Those may affect the accuracy negatively. So we have to incorporate those device and circuit properties into the software simulation, and this tool can support that. And also on the chip level estimation, we include all the peripheral circuits into the considerations, including the ADC, buffer, interconnect, DRAM access, and so on. So we can have a holistic estimation on the chip level performance, considering all the peripheral circuits and the communication overhead. So with this benchmark tool, let's project a fake 7nm RRAM process. We call it fake because there's no 7nm RRAM process available today. The best RRAM process reported in the literature will be 22nm process. So here let's show the 22nm RRAM as a baseline, and then also we show the 7nm SRAM as a baseline. Those are available in today's literature, and here we project a fake 7nm SRAM, 7nm RRAM process. So here we want to show that the area, latency, and energy. So here we show the cases with the max sharing 8:1 or low max sharing for the computing memory macros. So the conclusion from reading those plots tells you that compared to 7nm SRAM-based computing memory, the 22nm RRAM computing memory does not yield any advantages in latency and energy, and also it occupies a much larger chip area simply because it's an older technology node. So it seems that RRAM has no advantage compared to the state-of-the-art SRAM for the computing memory. This is because the computing memory has a lot of peripheral circuits. If we stay with 22nm process, then the bottleneck will be the peripheral circuits. We cannot unleash the potentials of the RRAM technology. Therefore, if we can scale the RRAM technology to 7nm process, here you see that the area can be smaller than the SRAM-based counterparts, and also the latency is comparable, and the energy is much lower. So here, the conclusion is that we have to scale the 7nm RRAM in order to outperform the 7nm SRAM. However, there's a challenge. The RRAM process needs a high write voltage, higher than the logic VDD, typically like 2 or 3 volts, to write the RRAM data. Therefore, RRAM may not be scalable to a 7nm process, as we see in the near future. If the RRAM stays at 22nm only, what would be the solution to further improve the RRAM performance? So our answer is this monolithic 3D integration. So the idea is very straightforward. Since we cannot scale the RRAM to more advanced technology node, let's stay at the 22nm process, because we need those high voltage transistors in the level shifter marks to drive the RRAM for the write operation. But for the other peripheral logic, like the ADC shift net buffer, we can scale that to more advanced node at 7nm. If we can have this partitioned design in the 3D fashion, then we can fully utilize the RRAM's benefits and also the benefit from the advanced logic. So here we do require there's active transistors on the back end to drive the RRAM array. And here we would propose some of the backend of LAN embedded FET, for example, based on the oxide channel, can serve as those high voltage driver to drive the RRAM array as a backend. So this may open up the space as a bottom substrate to allow more ADCs to further improve the throughput, because now we save the space by 3D folding. So if we do so, here we evaluate the benefit of this monolithic 3D integration with a hybrid node, RRAM at 22nm, advanced logic for the peripheral circuit at 7nm process. So here we show that if we do the 3D, then we can achieve much smaller area than the 22nm RRAM baseline, and also we can achieve much improved energy efficiency, compute density, and the power density. So here the wear density between the two tiers is estimated to be like 10 to the power 5 per millimeter square. So this does require a fine pitch integration between the two tiers. So the pitch is about like micrometer scale. So this requires the monolithic 3D integration techniques. Next, we are going to show the benchmark for the training, which is a more complex application than the inference. So there might be one question: is the symmetric weight update required for high training accuracy? So here, if we want to use the RRAM device as a weight element, we need to have multi-level states for the training, because training requires higher precision in the weight. But most of the RRAM devices reported in the literature may show this kind of non-ideal weight update behavior between the conductance versus the number of red pulses. When the conductance increases, it may follow the blue trajectory. When it decreases, it may follow the red trajectory. Therefore, there's a asymmetry and nonlinearity built into the weight update. And if we have the asymmetry in this black curve, we show that the accuracy will quickly drop as a function of the nonlinearity levels labeled from the 0 to 8. So here we analyze what's the reason behind this behavior. So we do see that here, if we have this nonlinearity, for example, if the next weight update requires a sign change from the positive to the negative, it will follow this red trajectory. Therefore, the conductance will jump back to the middle of the conductance range. So statistically, most of the conductance will be concentrated in the middle due to the asymmetry. This may not achieve the best optimal energy landscape during the objective function optimization. Therefore, we introduce a momentum factor to record the momentum of the weight update trend in the past few steps. Therefore, we can keep increasing the conductance even if the current gradient suggests a sign change, but we have to consider the previous few gradients. Therefore, if we employ this algorithm technique, we see that we can achieve a fairly robust training accuracy even under a very large nonlinearity level with asymmetry. So 89% Dixie button training accuracy is still achievable. However, if we evaluate the in-situ training accuracy with those reported analog RRAM in the literature, we still see most of the devices suffer from the training accuracy. Part of the reason is this large nonlinearity and asymmetry. Part of the reason is the large cycle-to-cycle variations, which may overwhelm the gradient calculation from the software ideal values. So here we would argue that to train the deep neural networks with the reported analog RRAM, even they may report like 5-bit, 6-bit, or 7-bit per cell, it will be quite challenging to achieve the same accuracy as the software baseline. Therefore, the alternative solution to the training would be this hybrid precision synapse. For example, here we show a concept of the 5 transistor plus 1 capacitor to store the LSB of the weight, while we use the RRAM to store the MSB of the weight. So here, for example, the weight, 8-bit weight, split into the 2-bit MSB and 6-bit LSB. So the 2-bit MSB stored on those 2 RRAM cells, and the 6 LSB stored on this capacitor as analog voltage. And we can charge and discharge this capacitor using a pretty linear conductance change by the charging pulse and discharging pulse. So the LSB will be volatile because the data on the cap will decay over time, but during the training, we are going to frequently update the LSBs. Therefore, it's not a big problem as long as the cap can hold the charges for like milliseconds. So with this hybrid approach, then we can achieve software comparable accuracy as experimented in our simulations. So like 91.8% can be achieved for CIFAR10, and also we can report like 18 TOPS per watt energy efficiency for the training, because most of the weight update will happen on the capacitor instead of the resistor. Lastly, we can estimate the cycling endurance requirement for this hybrid precision Synapse. So for example, let's assume the following assumptions. So here the conclusion is that we only need like 750 cycles for the CIFAR10 training, and also like only 20,000 cycles for the ImageNet training, because most of the write events will happen in the capacitor, and once in a while we need to transfer the LSB to the MSB, then we do the write operation on the RRAM. So the endurance is no longer a problem for the training as well. This is another benefit of this hybrid precision Synapse. And next, we are going to showcase a prototype test chip using TSMC 40nm RRAM process. So this is our recent design of a 128 by 128 RRAM array with all the peripheral circuits to do the computation. And here the process is the TSMC 40nm RRAM process as reported in this IEEE 2018. And here we show the diagram of the test chip, and the white boxes here are the digital blocks, and then the gray box here are the analog blocks. So here are some new features of the chip. We can enable the adaptive input specific control, reconfigurable with precision, integrated digital compute units, on-chip ADC references, and the write verify controller and embedded security. We will briefly discuss some of those features in the next few slides. Security is one of the new concern of the computing memory chip, because the neural network stores the weights into the memory array. If the adversary reads out all the memory data, then the adversary may reverse engineer the neural network model, which is valuable because the neural network model needs like weeks of the training with the GPU and with a private data set. So we don't want the adversary to read out the memory bits from the computing memory chip. What we can do is to add an XNOR cipher to encode the weight into a complementary pattern. So only when we have a correct key, then we can detect which row to turn on to read out the correct weight value. So here we apply the key to the input instead of apply the key to the weight. So we can still preserve the parallel computation in the computing memory. So here we did some analysis on the random guess attack. If the adversary uses a random key to decrypt the chip, then the accuracy is pretty low, depending on where the key is inserted in the neural network model. Because this is a ResNet, there's some bypass feature, so some layers will be more effective to be protected than the others. If we protected a few layers out of these 34 layers, then we can ensure the accuracy under attack is pretty low. And finally, on the right-hand side, we show the summary table of this chip performance. And here the clock frequency is 100 megahertz, and the reported energy efficiency is shown in here. And also we reported the CIFAR10 accuracy in the normal operation, and also the energy efficiency and compute density. There are some new features of this chip. So here we can enable the on-chip verify and on-chip references. So here, the previous test vehicle we showed earlier use off-chip verify. So we have to read out the cell resistance using the equipment and then do the write pulse again. This will be very slow if you want to program the whole array. So here we speed up the verify process by the on-chip circuitry, and we can detect the resistance by this dual SYM, and then we can tighten the distribution within this 200 ohm window. And also, there's another challenge, that is the ADC may have the offset due to the process variation. So here, what we can do is to use the dummy array to fine-tune the dummy resistance to adapt to the variations or offset of individual sense amplifier. Therefore, we can have a more uniform ADC output between the measured output versus the ideal output. So those are the new features of this test chip. Here, I would like to summarize. Computing memory saves the intermediate data movement, thus can improve the energy efficiency and throughput. And we say computing in SRAM is still a viable solution at an advanced technology node because it offers good energy efficiency and throughput. RRAM can be turned into multi-level states. That means higher density than the SRAM if it at the same technology node. And also it can offer the benefit of the no leakage and the non-volatility for the edge computing when the standby is often, because SRAM will leak over time for the standby power. Monolithic 3D integration, as we discussed, the RRAM on top of the CMOS as a hybrid node could fully overcome the challenges of the RRAM and fully unleash the potentials for the computing memory. DNN plus NeuroSyn is an integrated framework for benchmark different technologies, and that is open source to the community. And RRAM computing memory macro tape-out, as we practiced with the silicon data, could suggest the challenges and the promises of this emerging computing paradigm. With this, I'd like to thank my collaborators in the XNOR RRAM tape-out, Professor Jason Seal from Arizona State University, and also all the students and postdoc involved in this research. And I would acknowledge the support from the funding agencies, including NSF, SRC, and the Ascent Center, which is the SRC and DARPA Joint Program Center. Thank you. I would like to take some questions.